You already, I think, have demonstrated that you know what's interesting in physics at the moment by choosing this course. But it's always good to have some confirmation. So I'd like to start out with a little pep talk on why quantum computing is such a hot issue at the moment. I'm sure you've all seen headlines in the newspapers. It's one of the daily newspapers in Germany, for example, for a while had at least one article on quantum computing a week. You've probably seen news on quantum computers by various big companies like Google or IBM, breaking new records in their computing power. And also, I'm sure you're aware that there are various companies that are looking into applications of quantum computing, including, for example, here in Germany, various major car manufacturers that are looking at quantum computing as a way to solve complex optimization problems. Now, the basic physical principles underlying quantum computing, and we will go into that in more detail in the course, are twofold. One is the superposition principle of quantum mechanics, which means that the basic computational unit in a quantum computer is no longer a classical bit, which just has binary values 0 or 1, but you have quantum mechanical bits or qubits, and they have an entire continuum of possible states. And we will see actually later today that a nice way to visualize that is a sphere. And you can imagine the classical 0 and 1 states as the north and south poles of that sphere. But there is a whole continuum, namely the surface of that sphere, which are also possible states of the quantum mechanical bit. And this gives many more possible states that can be used in the course of a quantum computation. So this is one physical principle. And the other one, which we will also start discussing today, is entanglement. Entanglement means that when you look at two or more systems, here symbolized by the two spheres representing two qubits, then the two qubits combined, they can exhibit statistical correlations that are impossible classically. And the states that these two qubits can take are many more than just combinations of single qubit states. So it's not just, I don't know, qubit A is in state 0, qubit B is, say, in some superposition of 0 and 1. But there can be combined states of the two, which cannot be sort of separated into states of the individual qubits. That's something that we will start looking at today. And as I said, this gives rise to statistical correlations, which classically are impossible. And we will find that this is a potent resource for quantum computing. So a lot of algorithms make use of entanglement. The downside is when we talk about practical implementations of quantum computing, that these entangled states are very difficult to produce and very difficult to control. And this is actually the reason why it's only recently that quantum computing has really picked up, because there has been a lot of progress in experimental techniques and in the ability to control and manipulate quantum states. I show you here a particular example. This is an ion trap, also known as a Powell trap, and so you have magnets and you have electromagnetic fields controlling ions, and they are lined up essentially in one dimensions, and you have these electrodes that keep these ions in the trap and ensure that they can move in one dimension only. So they form a string, and the spacing is typically a few micrometers. Now, then you have laser beams that, on the one hand, cool these ions. So you want to minimize the thermal motion of these ions. And then you can use laser pulses to individually address and manipulate these trapped ions. And this allows you to implement operations, the kind of operations that you also need in a quantum computer. So the kind of transformations that you need in a quantum computing algorithm. And then at the end of such a sequence, you have to read out the final state of your ions, of your quantum systems. And this is done by means of resonance fluorescence. Now, this is really difficult and demanding experimental physics. And as I said, it's only recently that a lot of progress has been made. And in fact, in 2012, the Nobel Prize was awarded to Serge Laroche and David Wineland for developing many of these experimental methods. And that's really the prerequisite, has been the prerequisite for progress in practical quantum computing. Now, I should emphasize that this is not just about computing. There's a whole range of technologies that are now being developed, and quantum computing is just one of them. There's another field which is, of course, closely related, and which we will also discuss in this course, and that's the field of quantum communication. And in particular, this is relevant for security, so cryptography, and there are quantum protocols that allow you to communicate in a way that is physically secure and protected against eavesdropping. There's another major field of quantum technology about high precision measurement. So measurements of very weak magnetic fields, then quantum clocks is, for example, is a big field of research. So all this area of metrology benefits a lot from this progress in quantum technology. And then finally, of course, there's quantum computing proper. And there are two basic types that we will encounter in this course. One is gate-based quantum computing. The other is quantum simulation. So these are different variants of quantum computing. And so this is part of a bigger picture. I found here on the website of the Federal Ministry of Education and Research, they have a big program on quantum technology, and there's there's a figure that tries to summarize the various aspects of quantum technology. And you can look at that at home and sort of get an overview of what's going on in the field. Now, as people are progressing with these technologies, this is becoming increasingly relevant and important also for industry and for commercial uses. And I just want to give you just a panoramic view of sort of what's going on in the world. If you look at research efforts, I found this this nice graphic here, which shows the number of publications in a certain period as one metric for sort of the research activity for various countries. You see that Europe is quite active in research. You see here papers from Germany and Britain, and then there are also others which are not mentioned here, and other leading countries in research are obviously the US, China, Canada, Japan. When you talk about commercialization, one measure of that is the number of patent filings. And here you see that the US and China are really charging ahead. Here Europe is unfortunately not doing that great. But you can see sort of in recent years, this has really picked up and it's becoming increasingly relevant for commercial uses. There's a lot of investment going on worldwide at the moment. This graph is already a bit old. It's 5 years old, but already the numbers are quite significant. This tells you in millions of euros the R&D spending of various countries. Again, you recognize the big players, and you see that there are major sums involved, especially in particular regarding Europe and Germany. There's now, since last year, a major European program. It's called the Quantum Flagship. It's funded by the European Union. I think it's one of only a handful of flagship projects in research and development in Europe. And the European Union will dedicate €1 billion over a period of about 10 years. And it's quite interesting if you want to learn more about that quantum flagship. It's quite interesting to look at the website of the quantum flagship, where you will also find tutorial material, announcements of interesting conferences, progress reports, and so on. So this is also an interesting place to look if you want to learn more about research activities in Europe. In Germany in particular, there's also a national program on quantum technologies. It's also quite a major investment. I think it's, it says it's 650 million euros over a period of 4 years. And here too, there's a dedicated website. Let me open it for you, where you can find information about activities in Germany, also about companies, for example, that are involved in Germany, but there it is. Okay. Yes, I allow cookies. So this is a website on quantum technologies in Germany, and here you also find a lot of interesting material. There are also things like here, for example, the Quantum Future Academy. This is a program for people like you who want to learn more about quantum technology and work in that field. So I can recommend to have a look at that website as well. I mentioned already, lots of companies are getting active and involved in that field. And now I'm not going to go through all of this in detail, but once again, on the Quantum Flagship website, you will find a page on stakeholders in Europe. There's a directory of companies working on quantum technology in Europe, and also universities, research groups working on quantum technology in Europe. So that's a good place to get an overview. I show you two more links outside of Europe. There's one, I think, that's based in the US. It's called Quantum Zeitgeist. Interesting name. Zeitgeist is one of the German words that cannot be translated into English. And there you have news about the quantum technology community. And there's also a section on quantum companies if you are interested in that. And another one, here is the Quantum Computing Report. It's like an online journal that seeks to connect different members of the community from academia, from various companies, and there's also a section on players in that field. Now, all of this means that so there's a lot going on, and all these companies and research institutions, they need young people like you. And you see the headline from the New York Times some time ago. Companies and research groups are looking for young talents, and this is a field where you can really have a nice development and nice, interesting perspectives. That's also the reason why, for the first time in such a European program, the Quantum Flagship has a dedicated program or dedicated work stream on quantum education to train young people like you to get involved in that field. Okay, so this is this was a little bit of pep talk about your about what's going on in the field and how interesting the perspectives are for young people like you. But for me, at least for me personally, this is not the only reason why I like to teach this course. I like to work in that field. There's also just beautiful physics, just independently of career prospects and possibilities to earn money. It's very interesting physics. And I think that quantum computing and more generally quantum information processing really provides a new perspective also on quantum theory itself. So when you learn about quantum computing, you automatically also learn more about quantum theory, and it's just really interesting physics. The traditional way that you learn about quantum theory is that you start with experiments like the double slit experiment. You learn that electrons sometimes behave like a wave, so that there's a duality of particles and waves. Yeah, or you learn about the properties of atoms, that you have discrete energy levels, discrete emission frequencies when you do spectroscopy. So you learn about quantum theory. You view quantum theory as a theory of matter, of microscopic matter. Now, when you learn about quantum computing, what you will see is that quantum theory is also, or can also be regarded as a framework for information processing. So we will look at quantum circuits that might look like this, for example. You have quantum bits coming in, you have logical gates performing certain operations on these quantum bits, and then you have an output. So you do quantum information processing, and in a way you can actually view quantum theory exclusively as a way of doing information processing. I showed you earlier these textbooks that introduce quantum computing to a non-physics audience. And indeed, this is a possible perspective on quantum theory, that it is nothing but a framework for doing a new kind of information processing. And in a way, this makes quantum theory, this is a lot simpler than the matter picture of quantum theory. First of all, you will see that the mathematics involved is rather simple. We will only work with finite dimensional systems, so we don't have to solve differential equations. There's no Schrödinger equation. There's no infinite dimensional Hilbert space. We just have qubits in two-dimensional Hilbert spaces, or if we have several qubits, then they are still finite dimensional Hilbert spaces. So the mathematics, in a way, is a lot simpler. And we can do this kind of information processing in a way that completely abstracts from the material substrate. It doesn't really matter which physical system carries the quantum information, if it's a spin, if it's a superconducting qubit, whether it's a photon. All the interesting insights into quantum information processing are really independent of the matter that is carrying that information. And this is precisely the reason why also non-physicists are getting involved in quantum computing, especially computer scientists are now getting very interested in quantum computing as well.